Okay, so yesterday, and again, I really got to thank you so much, Mike, for being able to help teach these guys. It's pretty awesome that I have a chemistry guy in the room when I'm sick. Um, let's do a little bit more review of what you should have covered yesterday. Grab a blank sheet of paper, maybe write this up in the top corner on the back side. Let's make up a few pretend molecules, and let's see whether you can either name them or draw them. That's really the two main things. If I give you a picture, can you name it? Or if I give you a name, can you draw it? So why don't I do two of each as kind of a warm-up exercise? So here's the first one. Let's do this. So I'll make that one 1. We'll do that one. And then let's do a 3-methyl pent 1-ene. Let's do cyclobutene. Okay, there we go. So write these ones down, and then while you guys are working on this, let me give you some feedback on how this is going to work on the diploma. On the diploma, they cannot ask you to draw something. It's just not a possibility. So what they'll do instead is they might make it numeric response. And so on number 3 right here, here's what they might do. They might say, how many carbons do you need? How many hydrogens do you need? How many oxygens do you need? And they'll make it numeric response. Now, since we haven't even gotten to the spot where we're including oxygen or nitrogen yet, I'll tell you right off the bat, you don't need any oxygens here. But like that might be how they test you, is since they can't actually make you draw the molecule, they might say, how many carbons are there? And you might say, well, there's 5 carbons and 8 hydrogens or something. Whereas they can give you a picture of a molecule, and then from the picture of the molecule, they could ask you, well, what is its proper name? So anyways, why don't you guys take a try at this? See whether you can do that. I already realized I made a mistake somewhere. Can someone point out how this first molecule here, I've totally butchered it? This first molecule here, there's no physical way I can actually make this molecule work. I made a huge mistake on it. Yeah, I can't have a branch here. Why can't I have this branch right here? Yeah, I have too many bonds. There's 1, 2, 3, 4, 5 bonds here. So I've actually seen a question by the way before where they asked you which of the following molecules is physically impossible or done incorrectly. So it's a good thing I didn't intend to make that mistake. Why don't I make that a double bond? Now it's logical. So what's that? Won't matter if it's a cyclo. Yeah. Yeah. That's actually the point I used there. It's always tricky when you do the second ones there because you got to do it in your head and be like, did I screw it up somehow? Yeah, because you wouldn't need to have a number on that. But throw anything else on it, and then you would, right? Okay. Oh, okay. Like on that last one right there. Okay, so you wouldn't even throw the one there. So if there's no number 1, it's implied that it's on the one. Okay, yeah, that makes sense. That's not how our rules work. Because you wouldn't have thrown the 1 on the inside, you'd have thrown the 1 in front, and then yeah, I think I've seen it before because we sometimes don't include 1s on other functional groups because like carboxylic acids, we don't have to throw a 1 on it because the carboxylic acid has to be on the end of the branch. So, yeah, I took a video from last year. Yeah, I posted it. Yeah, yeah, that's okay. So in terms of things you're hoping to do if you're kind of stuck here, first find the longest branch you can. And I use a highlighter at first just to help out. So like on this first guy here, how many in a row can you find? Uh, looks like you can find 5 in a row. So then in terms of naming it, what's 5? Pent. Okay, then you have to identify what takes priority. And for us right now, if it's a double bond, that takes priority. Later, when we talk about other functional groups involving nitrogen or oxygen, that'll take priority. So for right now, what takes priority is this double bond right here. It needs to be given the lowest numbering system you can give it. So as I start numbering from either right to left or left to right, I got to make sure this thing's as low as possible. So if I go this way, it would be after the 2. So I could call it a pent 2-ene. If you started numbering from the other side, it would have been a 3, but I want the lower number, so that's a pent 2-ene. Once you've done that, the only thing left to do is take a look at what's left, and you have this little group up here and this one down here. Those are both methyls, because they're groups of 1. So in terms of naming it, at least our naming scheme that we use would look like this. On a 2 and on a 4, you have a methyl, but because there's 2 of them, we call it a dimethyl. The di is not because of the number 2. The di is because there are 2 of them. That makes sense? Okay, the next one here is a bit different because it goes in a circle. You guys know what's different about when you put it in a circle? What's the only change you make? Yeah, you literally put the word cyclo in it. So I'm going to try to find the largest group I can. That would be right there. So how many do I have there? 1, 2, 3, 4, 5, 6 it looks like. So 6 calls it a hex. And then again, because I have a double bond, that's going to take the priority. So this is going to have to be a hexene. And then because it goes in a circle, I'm going to call it a cyclohexene. So that kind of gets us started. The next challenge we got to figure out then is, how do we number it? And I was just chatting with Mike here. The double bond always gets the lowest priority you can, and so it's going to get the priority of 1. So we're going to call it a hex 1-ene. So the question then is, are we going to start numbering it like clockwise or counterclockwise? I'm going to do 2 examples here. I can start going 1, 2, 3, 4, 5, 6, like that. That would work. If I did it that way, this little branch right here would be on the 3. But if I tried numbering the other direction, because again, keep in mind that the double bond gets priority. If I start going the other way and I go 1, 2, 3, 4, 5, 6, you see how this little grouping right here then would be on the 6 instead? So I want the lowest number I can get. So we're going to actually go with the red. So I'll just erase all the black ones here. And we'll go this direction here. So as you go around the circle this way, here's the 1. After the 1 comes the double bond. So here's the 1. After the 1 is the double bond. And then on number 3 is a methyl. So this one would be called 3-methyl cyclohexene. Does that make sense? You guys think you can do this by yourself? Is that anybody beat me to that, by the way? Oh, okay. Do you guys want some time to try the last ones, or should I just hop right into them? What was that? You already got them? Okay. So let's try it here. You've got a pent 1-ene. So I start when I do this with this part of the word. Pent means 5. Ene means you need a double bond. The question is, where do you want the double bond? After the 1. Now, there's more than one way of drawing this then. You can either draw it like this direction or this direction coming in. Why does it not matter which way you start? But like, why is there not really a difference in the real world scenario? Yeah, all you have to do is just spin it around, right? One of the things you got to keep in mind is that I'm trying to draw in 2 dimensions an actual 3-dimensional replica, right? I think he used his model kit yesterday to kind of show some ideas of how. Did you use it?
Didn't use it. I could use it.
You talked about it. You guys remember when you played with the model kits though, right? Like the actual way in which these things look is it's usually going to be like out of the page, into the page. You guys remember talking about that back in Chem 20? We're not doing that, by the way. That's not something we're going to cover. But I do need you guys to know that that exists. So when we draw it flat like this, is it actually flat? No, not even close. It bends all over the place. Just gonna close this door here. So Anyways, because of that, if you were to look at something from this direction or look at something from this direction, right? Like if you just change your perspective, it really doesn't change the molecule, right? So that's why I don't care whether you start from right to left or left to right. So you might draw this one slightly different than me. If I start numbering them 1, 2, 3, 4, 5, and I put the double bond right here, perfect. So long as then I put a methyl group sitting right there. So that's what this should have looked like. But if you had put the double bond sitting on the other side there, that'd be fine. And I drew the carbon chain going up, but like this would be equally valid in our circumstances here. If you drew a double bond there and drew that going down, it's the same thing. It's just been rearranged. Oh, wait, one last thing. In order to do this numeric response, then we better figure out how many hydrogens there are. So my shorthand of drawing it is that I just draw a little dash for every hydrogen. So like this needs 1, 2, 3 hydrogens, 2 more hydrogens, 1 hydrogen. This has got a double bond, so you only want 1 hydrogen, 1 hydrogen, 1 there. There's actually an open gap here. Did you guys talk about saturated and unsaturated molecules yesterday? The idea that like an unsaturated compound has like an open gap here for hydrogen that kind of gets left open. So I'm going to leave those ones open. And then don't forget about this bottom carbon though. It also has some hydrogens. So it needs 1, 2, 3 hydrogens there. So if I were to add it all up, it looks like I need 6 carbons. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that one's not there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Makes sense? Okay, last one's pretty easy. Cyclobutene just means you need 4 butenes in a circle. Basically, it's a square, actually, from our perspective. Why is there no number on the ene? Well, no, I do need a double bond because I did put an ene there, but since there's no other groups on it, there's no point in me giving a number to it. Sometimes when it's pointless to giving a number, we don't bother writing it because it's always going to be between the lowest number you can have, right? So as I start numbering, it's going to be 1, 2, 3, 4. We would never number it with like 1, 2, 3, 4 that way. So like, there's really no point in putting a number on that particular one because it's totally redundant. So sometimes we skip numbers. I'll give you another example here, and we'll move on to our notes for the day. If I were to give you this molecule right here, this one would be a propane because I can find 3 in a row. And then there's a methyl group here and a methyl group here. But you would actually just call this dimethyl propane. And we put no numbers on it. Can anyone explain to me why we don't need to put the number 2,2 in front of it? Why is the 2,2 not useful? Not because it's symmetrical. It's the only possible location you could put these groups. What if, hypothetically, you could, I'm just going to erase it so I can pick this up. Give me a second. What if, okay, I'm going to put it back here again. What if I tried to pick up this methyl group and put it right there? It's no longer propane. Because then you'd have 1, 2, 3, 4 in a row. You know what I'm saying there? And so because this is the middle molecule on a propane is the only logical spot you could put a group like that, there's no point in putting the 2's in front because you can't have a 1 methyl. As soon as you put this on the 1, now it's not a pro, it's a bute. You get that idea? So, anyways, we're going to work on practicing this. This is one of those sorts of skills that you just need. You need a worksheet or two just to try. So I'll show you my worksheets to try. On Monday, if things go well, actually, I usually do an activity where we go outside and I give you chalk. And if it's a nice day outside, we'll draw molecules with chalk out on the concrete or something. So we have class outside if it's nice on Monday. Okay. Questions so far? Okay, let's move on here because I've only got half an hour left. What we want to focus on now is adding to this chart. So again, we covered a lot yesterday. We talked about how to do single bonds, double bonds, and triple bonds, as well as cyclos. Today we're going to focus on a whole branch involving the benzene ring. And it seems a little strange at first that you would need to have a whole section based on this, but a benzene ring, as we're going to talk about in a few minutes here, is actually a very, very common structure. So let me start by showing you what a benzene ring looks like here. This right here is how we illustrate a benzene ring. It is a hexagon with a circle in the middle. Now, I haven't done this yet today, but sometimes we have a shorthand way of drawing things. You guys covered doing something like this, where if I were to draw like that, do you guys draw some of these yesterday? Just use sticks as like a shorter way of doing it. Did you get to that much, or?
I did one on the board.
Okay.
Like one that they'd already drawn out.
Okay. Basically, what it means is if I ever draw like a stick drawing, I'm not putting all the carbons in. So like this guy right here would be a methyl cyclohexane. This end stick right here is the methyl group. And then these 6 that were in like the hexagon is a cyclohexane. Or if I were to draw this, that's propane. What it's implied is that at every edge, there's a carbon. See how that works? So this guy right here is propane. Or let's do a few more here. What would that one be then? 1, 2, 3, 4, 5. That would be pentane. If I were to do this one here with a double bond like that, this one would now be pent-1-ene because it's still got 5 in a row, but after the 1, there's a double bond. So sometimes we'll do like stick drawings as a way of shortening things. The reason I want to point that out is that that's what's going on right here, is that this is a cyclo. There's actually 6 carbons going around in a circle. You don't happen to have enough stuff in there to make a benzene, do you? In your model kit? Think you can make a benzene while I talk about it here? Here's what benzene we believe looks like. Benzene's actually a very frustrating, challenging compound. You might actually know more than I do. Yeah, okay. I won't worry about it here then. Scientists discovered benzene, I don't even remember what year it was. Benzene's unique because it has this structure, C6H6. There are 6 hydrogens and 6 carbons. And chemists were able to know this because they were able to calculate its molar mass, and they knew that, well, this is how heavy it was. There's 6 of each. It was very frustrating for them to draw because they had to try to figure out a way to arrange 6 carbons and 6 hydrogens. I've got a couple of initial ideas as to how they did this. Here's one of them. They thought, well, let's put all 6 carbons kind of in a circle, and then to each carbon, let's attach 1 hydrogen. But there's a bit of an issue with this. You guys remember the octet rule? You have to have like 8 electrons or 4 bonds. Take a look at this carbon, like say right here. How many electrons does this carbon actually have surrounding it? Yeah, 7, which seemed kind of odd because every single one of these ones right here didn't quite have enough electrons to make it work. I'll even draw that out. If you try to do that, you go carbon like this, and then this one attaches to a carbon like this, that one attaches to a carbon like this, that one attaches here. What am I up to? 1, 2, 3, 4. I have a dot there and there, kind of attaches there, dot there and there, dot there and there. That's 6, right? 1, 2, 3, 4, 5, 6. And then you could have like 1 hydrogen go here, 1 go here, 1 go here, 1 go here, 1 go here, and 1 go here. But then the problem is that there's just 1 extra electron inside, and nobody actually has an octet rule field. But that was the initial idea. Maybe that's how it fits. Here's the problem with that, though. They had a brilliant idea. They thought, well, maybe there's double bonds. Maybe there's a double bond right here, a double bond right here, and a double bond right here. That was actually a great theory for the longest time, but my understanding is eventually when they were able to measure bond lengths, a single bond is like this far apart. And a double bond, hypothetically, let's say, is this far apart. The bonds in benzene, it doesn't go long bond, short bond, long bond, short bond. They're actually all the exact same length. And it's like halfway in between. Do you actually know the length? I used to, but okay. Anyways, what ends up happening then is that although this idea here is great, where it goes double bond, single bond, double bond, single bond, evidence exists that it's not a single bond or a double bond. It doesn't have the right length for either one. And so what we've decided to kind of do is go with like a circle in the middle. And the current theory, as far as I know, is that there's electrons in the middle here, and I think the word we would use is delocalized. They basically go wherever, and so they smear in the middle somewhere here, and we don't know exactly where they go, but we know there's enough in there to make this work somehow. But yeah, it's not single bonds, and it's not double bonds. It's kind of like it's its own bond, and it actually comes up so often that it's given its own shape. Now you may see this once in a while for benzene, but this is uh, it's a little disingenuous because this kind of implies double bond, single bond, double bond, single bond, double bond. But does that make sense as to why that's really not fair? Is that it doesn't have like a short bond, a long bond, a short bond, a long bond, a short bond. Like it doesn't have that sort of shape. We know that much, but it's one of the best ways to like represent it. Is there anything else you could add to that, or do you know more about benzene? Or? Oh yeah, then let's not even go that far. Yeah, fair enough. Okay, so here's what you guys need to know then. This is what we know for sure about benzene. It's got 6 of each, and they have their own unique bonds. Yeah, because this is what. Yeah, it's got their own like crazy stuff that's well beyond our course here. Yeah, this is the word I was using here: delocalized electrons that somehow are in there. Long story short, we're gonna draw this, and one day, if you learn enough, you'll. Anyways, yeah, one day. From now on, though, basically, if you ever see this thing right here, I need you to know that this is called benzene. It has its own unique length of bond. It's not single. It's not double. It's its own. Benzenes are actually highly reactive, though, because they have the ability to have 1, 2, 3, 4, 5, 6 different entry points. And so you can attach all sorts of stuff off of any of these locations. You know how carbon is very unique in that a single carbon has 4 kind of like sprouting off points? Benzene's even better than that. Benzene has 6. So you actually see benzene used in a lot of different molecules. I even threw some on my very, very first slide in our notes back here. And you'll notice here now that this right here is a benzene ring. It's not the method that I prefer. I like the circle method. But you can actually see this thing is very useful because there's 1, 2. This would be a hydrogen here then. If it doesn't show something branching off of it, it's a hydrogen. This would be a hydrogen. This would be branching to carbon. This would be branching to hydrogen. This corner would also be a carbon, by the way. So now that we've learned a little bit more about how this sort of looks, you guys hopefully know a bit about this process. This is going to be one of those functional groups that we're going to talk about later because it involves non-carbon and hydrogen things. Same thing with this one. But now you kind of get a sense of what's going on here too. So same thing right here, right? This branches off into 1, 2, 3, 4 directions. What's attached to these 2 things right here then if it doesn't say otherwise? Hydrogen. Yeah. If it has a line, like say this line right here, this corner right here, that's a carbon though. And this corner right here is a carbon, but these are all just hydrogens right there. Does that make sense? Okay, let's talk about how to name it. Oh, I'm way too far up here. So these benzene rings right here, you can attach a whole bunch of things off them like you can kind of see here. I think this is what I've been saying here. For our purposes, though, we're going to do a hexagon with a circle. Okay, that's what you should see. But if you ever do see the whole double bond molecule like that, that could imply, I didn't draw that one very well, did I? The one where you go double bond, single bond, double bond, single bond, double bond, single bond. That could imply benzene as well. Okay, find this slide here if you could. Let's talk about how to name them. There are 2 main ways to approach seeing something with a benzene. Either benzene is the main focal point, in which case we call it a benzene, or the benzene itself is kind of like a branch, in which case we call it a phenyl. I want to show you 2 examples here. See this one right here? See how the benzene right here is kind of the main focal point? And then here is a branch. Remember at the end of this line, what's at the end of the line? A carbon. This guy right here we would call methylbenzene. Because really, this is a benzene, and then attached to the benzene is a methyl. Why is there no number? It doesn't really matter where it goes, because wherever it goes, it's going to have the number 1. So let's just skip that. However, this one right here is given a different name. This one's called a 2-phenylpentane. And the reason why is that really your main group is right here. You see how like this is kind of your main structure right here? And then your benzene ring right here is kind of like hanging off of it. It's maybe more appropriate to say that there's 1, 2, 3, 4, 5 in a row like that. And hanging off of number 2, we call that a phenyl group. So those are the two main ways of naming it. Figure out whether benzene is like the main core and stuff is branching out off of benzene, or whether you got all the random stuff and benzene is like one of the things attached to it. We just consider that whole benzene now. I know there's 6 there, but we just call that a benzene from now on. We would never call it like a cyclohex something. Let me try some more examples here, though. So on this first one here, first thing we got to figure out as soon as we see a benzene is benzene like the core? Is it like the hub? Or is benzene like a branch? If you want a silly analogy, I think of like, say, cities. Is this like the downtown core? And then from the downtown core are these like arteries that kind of spill out? Or is this a suburb? So like here's the main branch, this is the highway, and here it's a suburb off the corner of the highway. Say that one more time. Maybe that's silly, but is this like the main downtown? So this is downtown Calgary, and then there's a branch that drives you to the north, a branch that drives you to the south, a branch to the east. Or is this a long highway right here, and this is just like a suburb off to the side of the road? This is like Colehurst maybe, right? This is Highway 3, and then Colehurst is off to the side here. Okay. So anyways, we got to figure out which one is which. Here it's clearly the hub, so we're going to call this one a benzene. And then we just have to number the branches off of it. So if I use my highlighter technique, and I've now accounted for all of this right here has been accounted for, there are 3 branches remaining. 2 methyls and an ethyl. Is that clear? There's 1, 2, 3 here. We want the lowest numbers we can possibly find. So this is not what to do. I wouldn't go 1, 2, 3, 4, 5, 6. Because that would not give me the lowest numbers. You know what I'm saying? What would give me the lowest numbering scheme? Where should I start? And which direction should I start numbering to give us the lowest possible number combination? I agree. And then if I go this way, this would give me the lowest possible numbering scheme because I would have a 1, a 2, and a 4. And that's the lowest combination numbers I could possibly have. Hypothetically, let's say you start down here at the bottom. You could have a 1, 3, 4. But 1, 2, 4 is lower than 1, 3, 4. So now that I've numbered them, the only other thing I got to do is make sure it goes alphabetically. So what comes first alphabetically, ethyl or methyl? Okay, so on the 1, you need an ethyl, E-T-H-Y-L. And on the 2 and on the 4, you need a methyl. But one more thing here. As soon as you have 2 numbers, you have to put a die in front of it. The die is not because of the number 2, it's because there's 2 of them. So the proper name for this, I'm sorry it's a bit of a mess here, it would be 1-ethyl 2,4-dimethylbenzene. That's how you name it. A lot of students, by the way, they actually really enjoy the organic chemistry section because, one, we're not going to do any math at all. Like, there is no molar mass calculations, there is no formulas in that sort of way. A lot of it's just naming, and a lot of kids, they actually find this kind of fun in a way because it's very like schematic. Once you get the idea, it's like, okay, I can do this. Did that make sense? Okay, let's try this one here. This one's the suburb. So in a way, we got to first figure out what the main branch is. And I think the main branch is right here. So we got to figure out like that highway that's driving past Colehurst. How many in a row do we have? And be careful on this guy right here. It's not 1, 2, 3, 4, 5, 6. Because they put a little trick here. they did a condense. See how there's 3 of them right here? It's actually 1, 2, 3, 4, 5, 6, 7, 8. You catch that? It's 1, 2, 3, 4, 5, 6, 7, 8. So this is actually an octane. So then we got to figure out the lowest numbering scheme. And I'll do the wrong one first, so don't write this down. You could go 1, 2, 3, 4 right here, 5, 6, 7, 8, which means you'd have a branch on 5 and 6. But you guys can probably see, right? That's not the lowest numbering scheme you can have. It's probably better to go 1, 2, 3, 4, 5, 6, 7, 8. So again, it's an octane. And then we just have to do these in alphabetical order. What is a C3H7 going to be as a group? Anybody know? What's a group of 3 as a branch called? It's called a propyl. A group of 1 is a methyl. A group of 2 is an ethyl. A group of 3 is called a propyl. So we need a propyl. That's the group of 3. Do you guys remember what the benzene ring's called if it's a group? Phenyl. And alphabetically, phenyl will beat propyl then by a little bit because pH beats PR. So it's a phenyl and a propyl, and then the only other thing we have left to do is number them. So the phenyl is on group 3, and the propyl is on group 4. You're going to call this a 3-phenyl, 4-propyl octane. In a way, some kids have compared this section somewhat to like biology, in that it's a lot more memorization of classification. And once you know your rules about how to classify things, it's less of an applied sort of thing in that like you have to do molar masses and calculations, and it's just like we'll just name this, right? And once you learn the naming scheme, isn't like that's it's very similar in a way to some grade 11 bio where it's like, well, the name for this is this, and the process for this is this. So I don't know. Some kids find the sections kind of like bio. Okay, I want to talk about isomers. You guys learned that word yesterday, isomers. The idea basically is you have the same stuff, but it's in different spots. So these are all isomers of diethylbenzene. Let's talk about this word here. Benzene means you have a benzene in its core. Diethyl means you have 2 ethyl groups. So here, you have an ethyl group here and here. Well, this would be the 1,2 diethylbenzene. This one here would be the 1,3 diethylbenzene. This one here would be the 1,4 diethylbenzene. They have the same stuff, but like the place you put it matters, right? And that's one of the amazing things about organic chemistry is that all 3 of these molecules, they have different properties. They are not quite the exact same thing. They might be similar, but they're not the exact same. All of a sudden you make one little tweak, and all of a sudden the drug goes from being this to this. One of my favorite ones, I'll show you guys later in polymers. Do you guys know what PVC piping is? Hard, rigid plastic. Do you guys know what saran wrap is? Okay. The difference between PVC and saran wrap, I believe, is a single chlorine changed where its spot is. And all of a sudden it goes from being this thick plastic that you use in your pipes to thin, flexible stuff. And all it has is just one little tweak. I'll show you it later when we get to it. But like their formulas are almost the exact same as each other. It's really cool. So, anyways, these are isomers. If you can imagine Lego pieces, I like that analogy a lot. If you could like imagine that this piece right here, you could literally lift it up and move it to another spot, that's an isomer. Okay, let's go backwards. They will not ask you to draw it, but they might ask you stuff about it. So I do need you guys to possess the skill of drawing something. Let's try to draw the 1-ethyl-3-methylbenzene. So whenever I draw something here, I always start at the end of the word. We are supposed to do a benzene. So let's start by just drawing a benzene ring. So a 6-sided hexagon, 1, 2, 3, 4, 5, 6, with a circle in the middle, implies our benzene. Now, I don't care which one you pick to be the number 1 branch. So it really doesn't matter. So randomly, I'm going to pick this one to be ethyl. Only I haven't drawn an ethyl. If I draw it with a line like this, I've actually drawn a methyl because there's one carbon here. But if I do that, now it's an ethyl. That's a really nice like shorthand way of drawing it. So this is an ethyl group right here. Now all I got to do is pick a direction, and on the third one, draw a methyl. So why don't I go this way? This is one, that'll be two, this one. There, that's a methyl. That's it, we're done. Okay. Now that being said, if they were to make a numeric response though, and ask you how many carbons you have and how many hydrogens you have, maybe we need to do a little bit more thorough here. So I'm just going to add a little bit more here. There's 1, 2, 3, 4, 5, 6 carbons in my main group. The ethyl makes it 7, 8, and the methyl makes it 9. So if it was numeric response, you'd have 9 carbons. Most kids I find do not struggle with the carbons. They miss a hydrogen somewhere. That's the most common mistake I find. How many hydrogens would this carbon need here to be considered full up? How many bonds does it currently have? It has one bond, so it would need 1, 2, 3 hydrogens. This guy right here currently has 2 bonds, so he'd need 2 more hydrogens. This carbon right here is where kids will probably make a mistake. Right now it looks like this guy's only going in 1, 2, 3 directions, and someone might say it needs another hydrogen. That is not true. That's not how benzene works. Each carbon has one branch it can use in a benzene ring. And this carbon has already used its branch. It's done. This one goes to a hydrogen. 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 But these 2 carbons right here, their hydrogens have been replaced with something else. So don't add an extra hydrogen on this little carbon right here, because these extra delocalized electrons that are hiding in there in those funky benzene bonds, they account for it. This carbon right here, though, does need a few more hydrogens as well. So if we don't lose count, then there's 1, 2, 3, 4, 5, 6, 7, 8 on the periphery, and then 9, 10, 11, 12. So numeric response, your answer would be 9, 1, 2 then if they asked it that way. Everybody follow? Okay. That's all I got. Here's what you guys need. You need practice, and I know you guys are busy with other things right now, so don't make this your first priority. Finish up your electrochem stuff, but eventually you guys need to put some like reps into practicing naming these things. So I've put a couple of different worksheets on my website here. On Monday, I think what we'll do, so long as the weather is nice, I'll have you guys print off this one, organic chemistry ones to draw. It looks like this. What I'm going to do is give you a whole bunch of different molecules here, like say benzene. And I'm going to ask you guys to go grab some chalk, go outside, we'll have fun, we'll just make sure we enjoy the sun, right? But we can stay inside if you really want. And I'll ask you, like, how many carbons and hydrogens are there in benzene? How many carbon, and I'll make it more complicated eventually, right? Like a 1-ethyl, 3-methyl, 2-phenylbenzene. What would that look like? Right? And so, like, we're going to build the complexity. And then sometimes I won't give you the name. Sometimes I will give you, like, a scheme like this, and you have to draw it out and tell me what its name is. Okay, so that's one place we can do some practice. I also have more in here. If you guys want to eventually print them off, naming organic compounds worksheet 1, I have some sitting in here. Like the first page is basically name the stuff or draw the stuff. The back page is name what's going on. Okay, but you guys basically need some reps. Believe it or not, I've actually covered enough for us to almost have our first quiz. I know that sounds crazy, but like that's why I want to do our first quiz late next week, is I want to give you guys a chance to try this. We're going to do one more lesson, and then we should actually do a quiz and try some diploma type questions so that you know how I'm going to ask you this stuff. Okay. You guys good? Cool. Okay, I guess you guys can probably take off whenever it's time to go here. It's pretty quick, isn't it? Time's class end at again? 47? Okay, you got 5 minutes, I guess. So. Okay, we'll see you guys next week, or in calculus, I guess.